Okay, welcome to our first lecture on advanced fluid mechanics. So, today's class would be more of an introduction to fluid mechanics, primarily trying to understand what is a fluid before we actually take up trying to understand the equations of motion and going ahead and solving. So, intuitively you do not need a formal lecture to understand what is a fluid. I mean, all of you can visually see something and have a feel of what you think is a fluid. You see things around and that gives you a clear idea of what would you think is a fluid. But if you have to quantify what you think is a fluid, there are different ways of thinking about it. So, you can go back to your elementary knowledge of physics where you think of things in terms of phases of matter. So, you know that you can classify objects in the pressure temperature diagram in terms of whether they exist in a solid state, a liquid state or a vapor state. So, if what you see on the video here, this is a video of argon which is solidified, and then in room temperature it exists in the gaseous phase. So, as you see that it is melting, so there is a rapid melting of argon that is happening here, and that is melting into the liquid state, which instantaneously turns into the gaseous phase. So, now if you think in terms of what would be the way we think of these things at the molecular level, because all of these things at the fundamental level are made up of atoms and molecules. So, at the molecular level, if I have to think in terms of what solids, liquids and the vapor state would be. So, the solid state, as you will see, would actually consist of the individual molecules being stacked up in a very orderly manner, and we will soon try to make this a little more precise what I mean by order. So, you will see them in this nice orderly manner for a solid. In the vapor phase, there would be the least amount of order in the system. So, the molecules would not be in any organized manner spatially, whereas when you think of liquids would be somewhere in between. So, they would not be as precisely arranged as in solids, and they would also not be as disordered as you think of in terms of gases. So, if you had to quantify this fact of how ordered the phase actually is, and this is again we are purely thinking of the static scenario. No force has been applied on the system. We are just looking at the static state and trying to see if we can distinguish between these phases of matter based on how the individual molecules are arranged. So, if you say that I have, let us say, just to make things easy, I have 5 molecules and you start to connect these molecules. So, you say that I am going to join these molecules and these are the distances, the 4 distances between, let us say, this particular tagged molecule which I label as 1. Similarly, for the second molecule you could do the same and you would have another 4 distances for the second molecule, and you can repeat this process to actually form all the possible distances between these sets of molecules. So, what you are trying to do, you are trying to find the pair distances between these molecules, and you can ask the question, what is the frequency of these pair distances? How frequently do your neighbor be placed at a certain distance? So, if you ask this question for a gas and say that I am placing myself at the origin, which is one single gas molecule, and where would your neighbor be? Now, in a gas molecule, so this is actually, I mean the size is d. So, the second molecule cannot penetrate through this particular molecule. So, you are assuming it like as a hard billiard ball. So, the second molecule cannot enter that particular reference molecule, but you can find the probability of finding your neighbor is equally likely at any distance. There is no preference of where your neighbor is going to be. So, this is something which you can measure experimentally. It is like sending X-ray into a material and getting back the scattered signal, and from the scattered signal you are trying to infer how are things arranged inside. That is one way of trying to understand what state of matter are you looking at. So if the state of matter had this kind of very nice single monotonic plateau, then you have a scenario like a gas, where all your neighbors, whether they are going to be at a distance which is 4 times your diameter, 20 times your diameter, or a million times your diameter, it's equally likely. There is no preference of where your neighbor should be. On the contrary, if you think of solids and if you pick up crystalline solids, your neighbors are going to be precisely at certain locations. So it's like students in a classroom when a class is going on. You would expect that all the students are in a particular location, and then if you were to map distances from your location on the bench, your classmates are at precise location during that period of the class. But if you were not in the classroom or you were somewhere outside, let's say you were in a playground, then you could have your friends at any distance in the playground. There is no preferential location where they are going to be located. So the solid state is a state where if you are trying to find out the probability of finding your neighbors, you are only going to hit a yes at certain exact points. So the x-axis is the distance from the reference molecule, and you see these spikes which are where your neighbors are located. So that's the story of gas and solids. For liquids, it's a little bit in between. You don't have as much disorder as a gas, but you also don't have as much order as you would have for a solid. So if you are trying to find the probability of where your neighbor would be, there is a certain kind of a preference of certain location, but it is not as pointy or peaky as you have for a solid. So you don't have the crystalline structure that you have for a solid, but yes, there are going to be a bias in terms of where you are more likely to find your neighbors than elsewhere. So these are things which you can get from experiments, which helps as a diagnostic way of identifying what your states of matter is. And obviously the limiting cases are in most scenarios idealized scenarios. You would have somewhere in between for materials. Now why does it end up being in this way? Why does it actually choose to arrange itself in this way? And to see that, we need to think in terms of interactions. That what would be the energy of interaction between these molecules to be in these particular states. So if you say that for the gas phase, where we were actually saying that my neighbors could be anywhere, there is an equal probability for them being anywhere. So there is no energy of interaction in terms of distance unless you are exactly overlapping with me. So you are moving around like a billiard ball, till and when you go and hit, there is absolutely no interaction energy between the two molecules. They move around freely. Only the instant when there is a collision do you realize, hang on, I cannot penetrate through the other molecule, so I rebound. So that's why you have an infinite potential energy, a barrier for you to overcome if it was exactly a hard sphere kind of a collision. Real materials will not be that way. Real materials would not be like a rigid billiard ball. So in which case you can get closer and closer, but there is a penalty for you to get closer. So this curve is basically going to become softer as you think of a real material. So the short range repulsion will be there. You cannot penetrate through the other molecule, but yes, it's not going to be an exact jump. But there is also going to be a long range attraction that you will have, which comes in due to what is known as a van der Waals being one of the examples. That each of these molecules, if they have dipoles, these dipole-dipole interaction leads to a net attractive interaction which is significantly long range. So if you are very far apart, there is a van der Waals attraction that the molecules are experiencing. When you are trying to approach each other, there is a repulsion that you have. So now how this picture helps us think of the three states of matter. So there is one more energy scale which you need to think of, which is basically your thermal energy scale. So if the system was at a given temperature T and Kb was your Boltzmann constant, then Kbt gives you a measure of what is your thermal energy scale. How much does the molecules actually fluctuate as you keep increasing the temperature. Now if Kbt was somewhere here, where you are comparing this thermal energy scale with the depth of that well. So that well, as you can see, because there is a short range repulsion and a long range attraction, because of these two, you have a well here which has a depth of u naught. So, if your thermal energy scale was significantly larger than the depth of the well, what would happen is you do not really have any feel for the attraction part of the potential. You are only experiencing the repulsive part of the potential, because only when you exceed kBt do you see this potential energy. So, when you see the potential energy, you are only seeing it when you have gotten so close to each other that there is a near field repulsion that is there. So, this is what will happen when you have gases. When kBt becomes comparable to the depth of that well, that is when you get liquids. So, the attraction, the depth of that well and your thermal energy barrier, they are now comparable. Whereas, if your thermal energy barrier was very low compared to the depth of the well, which means intuitively if you think of it, your temperature was low, the molecules were not fluctuating so much, in which case you are in the most condensed state of matter, which would be a solid state. That your well depth is significantly higher than how much you are able to vibrate around due to the temperature. So, this gives us that when you are comparing these two energies, one is the potential energy of interaction and the other being the thermal energy that is there in the system at that given temperature, you start to get a feel that as you are increasing temperature, the system has a likelihood of actually going through a change of phase. That initially if you were at a lower temperature, you were in a solid state, gradually you go to a liquid state and then you can basically surmount that barrier, and now that long range van der Waals interaction is no longer relevant. So, when you would have learnt about ideal gas, the first thing you would have learnt about ideal gas is that these are just purely non-interacting system. That is the first thing you learned about gas laws. When you are thinking of liquids, these long range attraction starts to become important, and they become extremely important when you are thinking of solid like scenarios. So, this is how you are thinking of the pure static state of the system. What would be the behavior of the system? You have not applied any force whatsoever to the system. The system is purely in a state of rest, and you are trying to sample the system and try to understand what is going on, what is there inside, to understand the distinction that you would get between the phases of matter. Now, we are not here to do the static problem. We are interested in thinking of mechanical response. We are thinking of fluid mechanics. So, the word itself is there in the title of what you are going to learn. So, our goal is to understand that what would be the mechanical response as we go away from the equilibrium thermodynamics. So far whatever I was saying earlier, that was to do with the equilibrium thermodynamics of the corresponding phase of matter. But now, can we make distinctions based on the mechanical response? So, once again, if you take a scenario of a bunch of molecules which are stacked up in a solid and you apply some force. So, here I have applied what we will learn in some detail later. We apply a shear force in the system. So, if I apply a shear force in the system, it is going to deform. The molecules are going to get displaced and they will take a deformed state. If you remove the force, all of these molecules are going to come back to their original position. So, there is some recoil or rebound that you are getting. It is like a rubber band that you stretch it, you leave it, it comes back to its original state. So, this is a pure, what is known as pure elastic or Hookean response, that you have an initial force when you apply, they get displaced, you release that force, you leave, stop applying the shear force, it comes back to its original state. For a fluid, you do the same thing. It is going to move, obviously, the molecules are going to get displaced under the action of shearing force. If you stop that shearing force, those molecules are not going to come back to this original position. So, it will stay. There is no distinction between what would be its state when you have stopped it from the state which was just prior to stopping it. So, this is one way where you see that there is an inherent what we call as elasticity in the solid, which would not be there in fluids. If you do a similar experiment where you take if you repeat the same thing where you take these solid molecules, you apply a shear force, So, once you apply the shear force, it is going to deform and it will stay in this deformed state forever if the force is not altered. So, you are maintaining the exact same shearing force on the system. There is no further deformation. So, it will come to a deformation and stay there forever. Now, if you do the same exercise for a fluid and you apply the shearing force, the molecules are going to get displaced and they will continue getting displaced if the force was sustained. They will continue to keep moving. So, when you apply a shear force, the deformation that happens in the solid is proportional or will be dependent on the shearing force. So, if the force is held fixed, you have a fixed deformation, whereas for a fluid, the deformation keeps changing, which brings us to something that you are going to see in terms of what we will, that if you plot the stress versus the deformation or the strain, it would be a linear response when it comes to a solid. Whereas when you are doing it for a fluid, the response will depend on the strain rate, the rate of deformation, which means if you apply a fixed shear force, the fluid molecules will continuously keep moving because the rate of deformation is what is a constant for a given shear force or shear stress. So, this will be a rate of deformation. So, this is crucially how you make a distinction between a solid and a fluid. So, when I am using the word fluid, I am basically clubbing both liquids and gases here together. So, the mechanical response in both the cases is quite different. Now, a question that comes about is this how all materials would be? Will all materials have this kind of a very sharp boundary between mechanical response for solids and fluids? Would it exactly be this way? So, there are various examples, but one which is quite fascinating is an experiment which is on now close to 100 years. This is an experiment in University of Queensland in Australia. It's called the pitch drop experiment. Very simple setup. There is nothing fancy in terms of what this experiment is trying to do. So, all of you would have seen or you are familiar with pitch, which comes from coal tar. I mean, when you see roads being laid, pitch is that very thick, gooey, viscous liquid that is there. So, you have a funnel in which hot pitch is poured. Then initially when you pour it, there was this kind of a bulbous neck that formed. They cut this neck and gradually as you cut the neck, there a drop starts to form. And if you wait long enough, just like any other drop that you might have seen, it will grow in size because due to gravity it is trying to fall, it will grow in size, disconnect and fall. Now, the question or what the experiment has managed to do by being probably what would be the most boring, but still giving you such insightful answers is, if you look at the time stamp of when these drops started to fall. So, the pitch was dropped 1920 or 1927. So, you can see the time scales. 3 years later they cut the stem. The first drop fell in 1938, which is 8 years later. Then 47, which is again around 8 years, it went on, and the most recent drop that fell, which was in 2014, that was separated by around 13 years from the previous drop, which means you are expecting the next one to fall sometime soon. The point being that for you to see a fluid like response, which is just a drop falling off, you need to wait more than a decade. So, the key question or the key idea is, it's about the time scales of your observation. how long should you wait in order for you to see a fluid-like response? Would you see a response? So, if you were making observation for this setup over few seconds or few hours, few days, even a year maybe, you would be tempted to think of this more like a solid. It's only when you have waited long enough do you actually start seeing fluid-like response. Another example, another couple of examples where you see these are glaciers. So, glaciers are also known as rivers of ice. So, if you were to just observe a glacier, you would not be thinking of glacier as a fluid-like medium. You would just think of it as a collection of frozen stuff that is sitting out there. But we all know that glaciers do flow, and whether glaciers do flow or not, the one classic example is to actually just collect observations, and that will show the front at which the glacier moves. And there are a lot of sped up videos which show the motion of glaciers. So, it's again a question of whether you have waited long enough in order to make your observations. The other classic example is for Earth's mantle or Earth's crust. So, when you do a rapid mechanical response, a rapid mechanical response would be earthquake. So, when you have an earthquake, the Earth's crust is responding like an elastic solid. So, there are waves that get generated, and the entire description can be done by viewing it as purely an elastic solid. But we know that over millions of years, this is actually flowing and evolving. So, there is a liquid-like response provided you are waiting long enough. So, all these scenarios tells us that the boundary is actually a very blurred boundary. We are going to study during the course materials as if there is a perfect fluid-like behavior, but nothing is going to be perfect fluid-like. So, that is an important caveat which should be there. Even though we are not going to go into detail trying to understand that what would happen when this same glass of water, would it behave like a solid? Would it have just a glass of liquid water? Would it actually have a solid-like response? We are not going to look into that kind of a deviation, but it is important to understand that those deviations will exist. So, how do we basically bring in or understand those deviations? So, this brings in another very key idea to study fluid mechanics, which is the idea of continuum hypothesis. So, if I want to understand that what are the relevant or what are the smallest length and time scales that are there in the problem. So, if I just take the example of gas, I will do this for gas, it is easier to do it for gas. The picture can be extended for liquids, but it gets a little bit more involved. So, in gases, when a gas molecule is moving, it just moves with abandon, there is no interaction. So, I am taking the ideal gas problem. So, ideal gas problem means there is no interaction, they just move freely in space until and when they go and bounce into another gas molecule. So, this gives us an idea what is known as the mean free path. So, the mean free path can be found for gas molecules based on the concentration, the ambient temperature, etc. So, typically in standard room temperature, if you work out what would be the mean free path of air, that would be around 100 nanometers. That is the reasonable estimate of what would be your mean free path. That is the distance it travels. So, now I want to find out how much time does it spend between two successive collisions. That is my objective. So, that is the time scale. So, one length scale that I have in the problem is the distance it travels between successive collisions, and the other object of interest is time scale between successive collisions. So, I have a distance it travels. Now, what I need is the speed with which it travels. So, for in an ideal gas, if I want to find out a scale for how fast is it traveling, that speed would be of the order of the speed of sound in the system. So, speed of sound again in STP, I can write it as approximately around 300 meter per second. So, with this I can construct a time scale which would be, if a gas molecule were to travel with 300 meter per second over a distance of 10 to the power minus 7 meter, so it's around few picoseconds. Is that what you are finding as the time scale? So, now you see that there is a length for you to think about, there is a time for you to think about. So, if your measurement or observations were bordering on these length and time scales, you are not going to view the system as a bulk or as a continuum. And also what you think of it as a fluid like response, you can see that there is a time scale between the successive collision which is around 3 to the 10 to the power minus 10 seconds. So, when you are making observations which are on very small time scales, the tendency of the system would be to give you a solid like or an elastic response. If you wait long enough, then it will give you a fluid like response. So, now you have a measure of what you mean by long enough. So, for a gas like system, or it will become even smaller for a liquid like system, with like water kind of a system, is that you need to make observations or look at events which are happening on very short time scales to see an elastic behavior of what you obviously think of like as a liquid or a gas. So, if you need water to have a solid like response, you need to actually look into events in water which would be at extremely small time scales. So, the example going back to Earth's crust, in that case the time scale over which you see the solid like response is the time scale that we are familiar with, of the order of few seconds or few minutes, and there the liquid like response occurs over a much longer time scale. Whereas materials that we are used to in our day to day life and we always think of as liquids, for those materials it's very hard to see a solid like response unless you make your probe sample very small time scale events. And this also brings about the question that when I am making measurements, if all that I have been saying so far, everything that I have been saying so far is where I am actually drawing molecules. We are basically individually trying to draw these cartoons of molecules and talking about what we think of is happening in solids and liquids. So, why don't we do this forever? Why don't we continue understanding fluid mechanics exactly as this particular picture? Because at the underlying level, all of these are just a bunch of molecules. If I am trying to understand flow of water through a pipe, it is actually a flow of water molecules going through a pipe. So, why is there a need for actually doing this class of continuum calculations? What is it that we mean? Why are we trying to talk about this continuum? So, this is something which is an important idea to keep in mind, because it is a hypothesis which we are going to work with, and you will see where is it going to become invalid. So, the starting point again, if I take for a gas, if I say that I have 1 mole of gas which is around 22 liters or 22 into 3 centimeter cube is what I have as a 1 mole of gas. This is going to have an Avogadro number of molecules. So, automatically you see that a liter of gas has 10 to the power 23 molecules. So, the first question is the ease of calculation, that if I want to take a liter of gas and I want to compute various things for that liter of gas, you need to individually track these 10 to the power 23 molecules and solve for their equations of motion and then try to get something meaningful. So, your question is, do we really need the information for all the 10 to the power 23 molecules? And the second part is that, is it feasible to do it? So, the feasibility is impossible. If you have to track 10 to the power 23 molecules individually and solve for them, that is beyond the capacity of what you would be able to do with most accessible computers. And thankfully, we don't really require information of all these individual molecules. So we are in a soup because we can't handle so many molecules, but we are in some sense saved by the fact that we are also not interested in what a particular individual molecule is doing in this room. I am interested in what would be the density of air in this room, what is the temperature in this room, what is the pressure felt by the walls in the room due to the air that is there in the room. These are, if I am trying to design air conditioning for this room, what would be the flow rate that would be there for that air passing through. I am not trying to track individual molecules. So this is where we are in an advantage, that we are not looking at individual molecules. But then this brings about that if I am making measurements, let us say I am making measurements of density. Where do I know that if I say that I am giving you the value of density, let us say I am using rho for density at a point in space, at an instant in time, I am saying using the word point. So if at a point I am giving you a value of density as let us say 1 kg per meter cube. What does it mean by saying it is at a particular point? Because if at a particular point mathematically, there may be a molecule, there may not be a molecule. If I use it in the strictest mathematical sense that I define a particular as a point, there is always a chance that a molecule may pass through it or may not pass through it. But we do not mean it in that particular mathematical sense. What you might have seen in an introductory course in fluid mechanics, you look at a small control volume. This volume is small enough that it contains a lot of molecules and you can make meaning of what is the value of density at that particular point. Now, how small enough is small enough? Like how small enough can be the sensitivity of that instrument? If you are trying to measure temperature, if you are trying to measure density, how small can the sensitivity be? So, if you say that the systems that you are looking at, the smallest systems that you are thinking of is of the scale of a centimeter, and the smallest measurement that you can do, that you are thinking of sampling measurements that are of the order of 100 microns. So, the sensitivity of your instrument is around 100 microns. So, let us try to work out how many molecules are we thinking of there. I am not thinking of 1 liter right now, I am talking about the sensitivity of your instrument. So, if your instrument has a sensitivity which is around 100 microns, so that is around 10 to the power minus 4 meter, right. So, I have 10 to the power minus 2 centimeter. Now, if I try to find out the volume of this particular object, so the volume of this particular object would be right. That is the volume that I have for that sample space. Now, if you ask the question that how many molecules you are going to have in that particular region, so I have 10 to the power 6, 10 to the power 23 molecules in around 22,000 centimeter cube. And if I am trying to actually find out what is the number of molecules that I am going to get, so you will land up with a reasonably large number of molecules. So, in a small volume that you are thinking of, your molecules that you are still dealing with is significantly large. So, if you were to make measurements of density and you define this based on the system size that you have or the size of the measurement device that is actually looking at, you will get a fairly flat plateau unless you approach very small system sizes. Because when you approach very small system sizes, then you can have a molecule or you may not have a molecule. So, if you are thinking of flow through a microchannel, looks like a microchannel might be fine. You can try again going back and computing the number of molecules that you have for flow through a channel of diameter 10 micron. Would be okay to think of it in terms of a continuum problem. But if you now think of flow through a nanotube, where the dimension has gone even further smaller, in that case, it's becoming doubtful whether you can still think of in terms of having very large number of molecules. So, you can continuously keep calculating the number of molecules that you will have typically in systems of that particular size. So, as the size starts to shrink, when you go to very small systems, then treating it as a continuum is no longer a great approximation. You are going to have fluctuation, and you can think of it that you can, even if you are thinking of density as basically trying to find out how many molecules do you have in a given volume, you can have at any point 5 molecules in a box that is made up of 1 nanometer by 1 nanometer by 1 nanometer, or you may have none. So, there is always going to be the fluctuations are going to take over. Similarly, if your measurement system size were to become very large, then large scale spatial variations of density also will start to matter. So, what we are talking about is when you are making measurements that will not look into very small scales where these fluctuations are no longer to be taken into account. So, that is basically the idea of continuum. So, we will define all quantities to be uniformly defined at every point in space at every instant in time. Even though we know that truly speaking at a given point in space mathematically, there may be a molecule of water, there may not be a molecule of water. But we are not looking at such small system sizes. At the scales at which we are looking at the scales that we are making measurements, we are going to have enough number of molecules that we can define a mean or a field quantity of velocities, pressure, density, temperature, all quantities. So, this is primarily what constitutes a key part of what we do as continuum hypothesis. And going back to the question that we had, that what do we think of as fluid? So, I gave various examples trying to justify that how we think of fluids, how we have fluids as examples based on their static structure, based on their mechanical response, and then trying to make a sense that if we have sufficiently large number of them, we can also define various field quantities there. But this, as I was already hinting at different places in between, can the idea be extended to things which are completely out of the box in terms of what we think of as fluids? So, here I have 4 entities. I mean, they on the face of it they appear ridiculous. So, you can, what you have is a picture of a bacteria on the one corner, then you have a sheep, then you have sand, and then you have a bird. Now, at the face of it, it looks outrageous that why, what is the connection of fluid with these individual objects? Now, if you think of sand, which is probably more relatable, you can have sand dunes which flow quite similar to how you would see flow of other fluid like material. Another example would be also mud, which is again made up of things that you can see visually. Molecules of water, molecules of gas, you are not able to see with naked eye, but grains of sand, mud particles, you are able to actually see in most cases with naked eye. So, in that case, the flow that you observe, the flow is quite similar to flow of a liquid. Then in the bottom you have what is a sandstorm that is having. So, the sandstorm is when you are looking at it, it's basically dust that is moving, behaving like a fluid, even though they are made up of individual dust particles. You can also think of cases now that these were examples related to these passive particles, because these are all sand grains or dust particles, everything is passive, they are being swept around by some mechanical forcing. There is wind or there is something that is blowing them around, and you see them in such manner. Now, this is the example of starling. So, you have these birds forming these flocks, and when you observe their motion, they form patterns, they form these large scale orders, which is not something that you will be able to identify from an individual bird. So the collection of these objects, and when I say objects, I am thinking of them more as objects which can actively move around. They create patterns that are more reminiscent of what you will think of happening in fluids. And the sound, which is known as murmuration, individual birds are basically making this sound, and you see this beautiful pattern that emerges there. At the underlying level, the question that interests many is, can you model it as a fluid? Can you model it based on how we are thinking of continuum? Can you think of this as a continuum system? The same question applies for motion at very small scale. So this is bacteria which would typically be tens of microns in size, and what you are observing here is in a channel where you can see roughly the scale of the channel in few millimeters, there is a pattern that is emerging. There is a convection pattern that actually comes about in this fluid. So with this, what we are not going to look into systems of this kind, but the point is you can define field quantities in such problem. This is the example for the sheep thing that I said, where again, very different from what we think of in terms of fluid molecules, but when you have these moving around in a flock, when you have them moving around in a herd, there is a certain sense of fluidity in them, and then that motivates the question that the underlying principles that we learn in terms of how we relate the motion to an internal stress and how is the stress related to a deformation. If you see the second video seen from a distance where you are not paying attention to the individual entity, it almost looks like a blob of fluid that is actually doing its own thing. So this is broadly the tools that are applicable, whatever we learn in our, so going forward we are going to focus primarily on fluids as we understand things like water, air, but the principles that we are going to develop to understand the motion of fluid, a lot of it can be applied to significantly different systems. So with that I will stop, and yeah, I think I can take questions. Yes.
On that page where you describing the potential and thermal energy, can you just
Yeah. Yes. U naught. U naught. This is just the depth of that well. So you have a repulsive part. So the force that you experience is the slope of this curve. This is the potential energy. So you have a repulsive force because the curve is going up. So that's your repulsive arm. So this part is repulsive, and this arm, which is increasing with distance, this arm is attractive because the slope is opposite sign. So this creates a well here. So the depth of that well is U naught. And what you are doing now, you are comparing the depth of that well with the thermal energy, because if your thermal energy was larger than the well, that means you are somewhere here. That's the thermal energy that you have in the system. So you already have inherently this much amount of thermal energy due to your own motion. The temperature leads to fluctuation and you have kBT energy. So you are never going to access the attractive zone. So you will not feel the long range attraction if your thermal energy was larger than U naught. Only when your thermal energy is lower than U naught do you realize that there is a possibility for you to also experience the attractive interaction if you are far apart. So this comparing the two scales helps you understand what state of matter it would be. Any other questions? Yes.
So what really happens at the separation when the potential energy is zero?
So the actual magnitude of the energy is not some, you're interested in gradients. So there is the force here I mean, so the system is basically responding to your potential energy well and competing with your whatever is your thermal component. So finally it is going to minimize that and arrive at a certain, so what you're seeing is just the potential energy. This plus the thermal gives you the total energy, and depends on what kind of energy you are interested in. Minimizing that will give you the state of matter that you would like to reside in. So the actual value is not something that you are quite interested in. You are interested because you can have a datum, you can add an arbitrary constant to it. It will not change your state. What you are thinking of is the gradient of it, and so wherever that gradient gets minimized is where that state of matter is what you will occupy. Yes. So you define it with respect to some datum there. Any other questions?
You mentioned the density fluctuations on that. Why the fluctuations happen in the small scale? Can you
Yeah. So for instance, if you say that I am measuring density, so if you think of density as counting, so the example which I always give is like, if I want to find out the number of students per square meter in a classroom. So right now let us say there are 20 students in this classroom. Okay. Now if I start making my class, or rather if you take this example of a classroom, the moment we all disperse, there will be no students in this class, right. So whatever I measure as the number of students per square meter in this classroom is going to be 0 at that instant. At the next instant when somebody steps in, you will have a large number. Now you think that you are going to measure this over entire CRC. So this room might be empty, but the adjacent room might have someone. So you are going to have less fluctuation when you have a system. The measurement volume, the control volume is becoming larger in size. When you have very small control volumes, if you are trying to do just a counting, then you may find a molecule, you may not find a molecule. You might find 4 molecules in some instant of time, you might find 0 molecules, you might find 1 molecules, which is why that fluctuation becomes very severe when the system size becomes small. But the system size becomes large, then over 10 to the power 23 plus 4 minus 4 plus 400 minus 400 plus a billion minus a billion, it means a small fraction. So the whole point is that the number that you have for 1 mole of any system, any material, is 10 to the power 23. So when you are thinking of system scales of that size, fluctuations are going to get smoothened out. But if you start shrinking the size, then is where you are going to get problems. Any other? Yes. Yeah, so one example where this always happens is closer to engineering, is when you are thinking of shocks. So when you have shocks in problems in gas dynamics or problems in aerospace engineering, the shock location is where you have a sudden jump occurring. So you have a small region over which there is a sharp transition that is occurring. So you can solve your continuum equations everywhere, but at that location you won't be able to solve continuum equations. So the correct way to do it, again, solving individual molecules is an impossible task. So you never try to solve individual molecules unless you know that you only have those many molecules. So for instance, if you are thinking of flow through a carbon nanotube, you are expecting that the number of molecules to be not as large as 10 to the power 23. You are expecting them to be much smaller. So in which case there may be a merit, or there may be some hope in doing a continuum calculation. But when you are doing it at the large scale, even when continuum approximation is breaking down, you solve for probabilistic quantities. You don't solve for the actual equation of motion. So you solve for the fact that what is the probability of finding a molecule at a particular location moving with a particular velocity at this instant in time. So that is the quantity that you solve for. So there is an intermediate approach that you use, which is in between solving Newton's laws of motion, F equal to ma for all molecules, and solving Navier-Stokes. There is a path which is in between, which says that if I have sufficiently large number to define some kind of a distribution. It's still not continuum, but I still have sufficiently large number to define a distribution. It's not 100 molecules, it's not 1000 molecules, but I still have large enough to define some kind of a distribution, in which case you solve for those distribution quantities. So, you say again, like, what is the probability of finding a molecule at a given position at a given velocity, with moving with given velocity at a given instant of time. And if that number starts becoming larger, then this will transition to your continuum equations. So, that intermediate equation is known as the Boltzmann equation. That is typically how we can formally go from a molecular picture to the continuum picture.